So this afternoon, I'd like to focus on, these are cumulative, you realize. If you've been here for the whole time, you can bring in anything that's been spoken about for the last 2 days. That's fine. But specifically this afternoon, we're going to look at one of the more challenging problems, which is capabilities, challenges, and progress for mobile operation on the lunar surface, and address these questions. And we're going to start with each of the speakers having a chance to say their piece because they've had to think about these questions. Before we do that, we'll probably have Rodrigo Romo answer the questions that we had for him. He is on the line now, as I understand. But then we will have each of the speakers address the questions. And here's the questions for all of you. What are the key architectural and financial elements needed to support surface activities presented during this meeting, or that you know about? Question 2, what are the current capabilities and limitations of your concepts involving lunar surface exploration, and progress anticipated over the next 5 years, particularly in terms of compactness and operation in a broader range of environments? And then describe the human-robotic interface, in particular considering how to use the human advantage in the picking up of, in a lot of ways, but one of them being, as an example, the picking up of truly representative samples. That means effective down select, by the way. I know it seems counterintuitive, but it means that you don't pick up every sample you see. You just pick up a small number that are representative. This is not random. It's not the same thing as randomly picking up samples, and it is what I call the Apollo effect, because that's basically what the Apollo guys did. So whatever strategies we have for robotic visits, there are ways to do this that don't involve humans having to be physically present in that environment. So all the kinds of options probably should be on the table. So to start, before we do anything, let's have Rodrigo Romo answer the questions that we had for him, that we sort of voiced and put on the record, but that he didn't get a chance to hear before because he's now with us. So I'll ask one, and then other people can follow. Mine was, what kind of strategies are the people involved in doing the robotic village considering to keep mass from growing large, which is the tendency with all robotic rover concepts I know. I was involved in a project at Goddard, and that's exactly what happened. So it's very hard to keep mass from growing when you get to robotic systems. So what are your strategies, Rodrigo?
Yeah. Can you hear me now?
Yes.
Okay, great. And first of all, thanks for having me here, and I apologize for the blunder before. Hawaii does not go into daylight saving time, so when I scheduled my meeting, I was an hour off for the current time. But anyways, I'm here now. That's a good question. Right now we're working the Robotic Village project is a multi-phase project. It's just started. We're in the very early stages of it. The first thing we've received is a platform for a mobile rover from Ontario Drive Gear, on which we will be testing different types of surveying and data sampling, payloads, and instrumentation. But you're correct. The size, the mass is the number one constraint that we have, and anybody has. We're going to be working with some pre-existing models of planetary exploration systems, such as like the Athlete platform and the pilot to retrieve oxygen from regolith. So we're not intending on reinventing the wheel. We're going to be starting with existing platforms that have been used and designed by NASA and other space agencies, and from there start collaborating with other space agencies and see what needs they have, so we can build the robotic village around their needs and their requirements and specifications. We're in a very early stage on this project right now.
I noticed that you specifically mentioned 3D printing, which could be a strategy, certainly to reduce the amount of material you have to bring with you.
Yes, that's a project we're really excited about. We're about to begin on it. We just had a laser shipped to us, and it's been stuck in customs for a couple of weeks. We finally got it clear. It should be arriving here in Pisces this week. But the concept will be to use regolith as the printing media. And we're looking at a couple of technologies. One is laser 3D printing. Another one is going to be sintering using microwaves. The idea is precisely that. It goes back to in situ resource utilization, using what's available on the moon or Mars. And turns out that the regolith, the chemical composition of the regolith that we have here in Mauna Kea on the Big Island of Hawaii, is very similar to that found on the moon and Mars. So we know that if we can be able to melt and form using the regolith here, that's going to open a huge world of possibilities for future development for 3D printing. First thing we're going to be doing in the very near future, within the next couple of weeks, we're going to be printing 3 sidewalk slabs, basically. And they're going to be placed somewhere here in Hilo, in the city of Hilo, and we're going to be evaluating their wear and tear, comparing them to regular cement-based concrete slabs, to see if the 3D printed slabs made of regolith will have the same endurance, rigidity, and physical characteristics that a concrete slab does. After that, the next phase from that will be to print a dome, which could be used as a shelter for a rover, a small-sized dome, just to start working the technology of 3D printing using the existing regolith or basalt here on the island.
Are there any other questions for Rodrigo? Yes, we do have one from Doug and from Tom.
I was curious on the microwave work on the regolith. Without the nanoiron, do you expect to have different characteristics between your experiments and what would happen on the moon?
You know what? If you have my email address, if you can send me an email, the short story to the short answer to the question. The microwave sintering is not my project. It's being run by a colleague of mine, Christian Anderson. But if you can send me an email, I'd be more than glad to put you in contact with Christian, and he can answer you the questions on the microwave and the laser. I'm more involved with the management of the project management side of the robotic village, which is getting the different technologies integrated into the mobile platforms. But like I said, send me an email, and my email is available on the presentation, right?
Yes.
Yes.
Okay. So
Thank you.
send me an
And
email, and I'll
Tom
be
Roth.
glad to put you in contact with Christian.
Generally, I'm working an idea called the Big Moon Dig, and it's completely consistent with what you're doing and just puts a new front-end story on it that makes it a lot less likely to get canceled. So I will email you with details on that. But one of the things that is necessary on this printing thing is we have to understand safety, and the best way to understand safety on them is ultrasounding the structure to look for flaws. So with your building, you need to have a Q&A capability, and I believe ultrasound would be your best bet. Thank you.
Yeah, I agree, and we are looking at doing some ground-penetrating radar work. You mean ultrasound of the foundation of where you're going to be building up?
Get a mic up.
Hello?
Was that a question?
Basically, if you put what I need is walls of a habitat. We couldn't trust them unless we can ultrasound them and show they're not cracked, and that's an easily doable thing, standard industrial process.
Yeah, then definitely do send me an email, please, because like I said, we're in the early stages of development of this project, and yeah, we'd like to work with anybody who's interested in developing this approach.
Other questions? Great. So let's start with the design challenge questions. We'll start with the speakers, and then from that we'll branch out into for everybody. And you can feel free to participate at any time. I'm just facilitating, getting the discussion started here. So Brendan, why don't you start with the questions?
Sure. So for the 3 questions, I'll do my best to answer them from the software perspective, software design perspective. So question number 1, what are the key architectural and financial elements needed to support surface activities presented during this meeting? So from an architectural perspective, the concepts that the concepts we kind of touched on in the presentation today These more efficient and effective, or we feel effective, design approaches, I think, are important from an architectural perspective, software architectural perspective. Concepts like platforms that enable modular reuse of components across missions, loosely coupled architectures that enable modules to be plugged in or pulled out to be tested early using black box testing techniques. I think are kind of key elements that'll be needed to support the more resource constraint spaceflight development missions for missions in the future, and not just surface activities, but certainly applicable to those as well. From question number 2, what are the current capabilities and limitations of your concepts for lunar surface exploration and progress anticipated over the next 5 years, particularly in terms of compactness and operation in a broad range of environments? So I see that we've seen a trend towards smaller, embedded, general purpose processors and systems. So processing boards, the group from NASA talked a little bit about the processing, the couple of flight computers that they have on board, the fact that they're utilizing Linux. We've utilized that in a couple of programs as well. I definitely think that that's the progression towards less, fewer rather, specific purpose processing units to more generalized digital signal processors with algorithms implemented in software, more generalized general purpose processors utilizing open source tools like Linux and components that are available to a wider community, and adapting those commercial off-the-shelf components to spaceflight. So I definitely see that as the as where things are headed. Not only in the lunar surface, not only in small sats, but certainly in CubeSat and other nanosat missions as well.
What about the trends in the CubeSat development to share resources?
Share resources across development
Share
teams,
processing resources. Well, on board in terms of the operational concept.
Yeah, I definitely think we're definitely seeing that as well. So, 15 years ago, we would see more of an, and I've heard, I guess, like I talked about in my experiences in the background. Back then, I was in the enterprise and internet world, but seeing projects that, and I've talked to others. By fairly specific or purpose-built pieces of hardware, that may be an overly broad statement because I haven't had, I don't have a lot of experience with those items. But what we certainly are seeing now is that when we're talking with different development groups, when we're looking at new missions, we're looking at what's available off the shelf. We're looking at pulling in components that we can go and purchase rather than design complete hardware up. Or components that we can put together that have the capability of in one part of a mission communicating at one frequency and then changing to another frequency by changing an algorithm in a software-defined radio, or handling attitude, tasking a processor to handle. Maybe more heavily making things up as I go, or brainstorming as I go here, but attitude control more in the beginning, but then perhaps more science processing later on. The point I'm trying to make is that the utilization of more general purpose processors enables us to change behavior of these systems, how they interact with their sensors and actuators by making changes to software. Versus having to go in and change out a hardware radio or change out a hardware component.
Using apps, basically, which Tom really likes to point out. Tom needs a microphone.
It's called anti-fragile.
Sure.
You have to go beyond robust, and we have to get into anti-fragile. When you're up at anti-fragile, you're gaining energy out of the chaos. You're sitting at the edge of chaos, and you're actually prospering, growing, pulling energy right out of the chaos. And that's where we have to be in the 21st century, or else our programs are going to get canceled. And it's quite doable, and feels things like that agile programming, that is a move in the direction of anti-fragile. Terrible term.
Abraham has a comment.
The project you mentioned, Sunjammer,
Yes.
would typically fit in a lunar cube style design that belongs to class B you mentioned. Any estimates on lines of code, the industry practice?
Lines of code is not a metric that we typically use. So I don't have an up-to-date number, total number of lines of code. I can speak a little bit to the fact that we have a team of about I would say 7 full-time software engineers that have been developing software on Sunjammer for a little more than a year. And so we're nearing completion of software development for that program. And one of the ways that we've been able to, and that's it's a fairly complex system with new forms of controls considerations for the sailful. And so one of the ways that we've been able to be effective and low cost in that mission is, like I mentioned before, we're following similar design patterns. We are looking to Linux operating system. We're looking to off-the-shelf libraries for doing things like encryption and compression of data, encoding of video, etc. We're not developing those things from scratch. We're pulling in items that we can find, or that we can find. We peer review most of the code that comes in from those outside sources, at least, but we're still able to leverage these off-the-shelf components, integrate them together. And so in total, in the current Sunjammer build, I'm not really exaggerating when I make a statement like, there's probably a few 100,000 lines of code that make up the functionality of the current spacecraft design. We wrote a small percentage of that.
Yeah, and to establish a rule of thumb, if that happened to be a class A mission or class D mission, is there like it would be almost double or 100 times or 1/10, going up and down the classification?
Yeah, so let me clarify one point just very quickly. Sunjammer is a class D mission, but they've classified our software as class B safety critical. And so we designed the software to a class B level. But other components of the spacecraft are a Class D mission. So when certainly going higher up, it's probably it certainly is exponential increase in the level of effort that's required. Not necessarily 10 or 100 or 1,000 times more code, but the level of analysis, the perhaps detail of design, but certainly the level of verification and validation that you would do in order to support a Class A classification versus a Class B classification versus C versus D. And so in our case, we peer review every line of code. We test every system, every subsystem at the black box level. But if we were a Class A, we would be testing every code path, every line of code. We'd be doing code coverage. We'd be doing a lot more effort, not necessarily generating a lot more software. Does that make sense?
So you do more testing of each component individually, as well as the whole integrated system.
Absolutely.
Well, this gets into a whole area of an adaptable interface, which is one of the things that I've worked on for a DARPA project with Mike Riley, and Abraham knows about it, so that you can actually incorporate any COTS pieces, but you have software that essentially connects all these pieces, observes the interactions, and eventually becomes a proto-intelligent decision engine. So it can adapt in a stable way to the demands and the environmental changes, moving away from strictly expert systems approach. Because as you know, of course, as you get more complex with expert systems, your potential to make a mistake or not find the error and not figure out a way to test it goes up a lot.
Right.
Because if you keep the code simple, it's easier. I mean, I'm getting my head around how to do agile scrums with with Class A mission software, which must be a major challenge.
Yeah, I mean, I could see how we would adapt our processes and techniques to a Class A mission, but certainly the area that there would be the widest impact is now that you've gone through and you've done a design, and as you're moving forward through calendar time, through your schedule, you could still leverage the ability to be flexible to some extent, but you get to a certain point, and your verification validation is significantly higher. Your teams are higher as well. I'll draw another very quick parallel. We've talked a lot about space because that's certainly the area that's most important to all of us, or most interesting to all of us in this room today. But we do have or have had aircraft system design and development as well, and so there are a number of parallels to the Class ABCD spaceflight to FAA DO-178B, or now C level ABCD and E. And so we've done entertainment systems, communications, internet on aircraft sort of things, and then further up, weather radar is one example. And similarly, we can take a lot of the same sorts of concepts, but as you move up that chain towards more safety critical items, how you peer review, how you pull in and integrate off-the-shelf components into your system, and then how you do verification and validation becomes really critical.
Yeah, so whether the protocols required by the government would let you do this or not, one of the ways you would use a Scrum methodology to speed up the process is in the early days of testing, is that you would try a lot of different models. And there are ways at that early Scrum level where you can fail a model just kind of by looking at it or putting in garbage data, or there are ways where you can quickly find flaws before you finish the complete design. And so by the time you're getting into actual testing and qualification, there's not much you can do anymore. That's the value of this, is that you can do a lot of learning very quickly early on, so that the intellectual understanding of what it is you're doing is far more mature than if you waited until you were in that detailed qualification to find your mistakes. And there's a style of early testing that can bring up those things that is not usually done, and certainly wouldn't be done in a top-down waterfall kind of model.
That is critical. The early iterative, low fidelity exploration of the trade space is really critical. And that's part of when we looked at this tool, which you call Frontier, that interface early on, that ability to do that is critical. And that can weed out things that aren't obvious at first, that might work or might not work for you. And you can do it at a low enough fidelity, so you haven't had to invest a lot of time and effort. So it's...
Yeah, and there's one other concept that I'd like to add in. It may not have been as clear from the presentation earlier. There's two other aspects to the lean space approach that we take, which is continuous integration and test early and often. And it gets back to kind of your point too, right? You try to when we do these sprints, we try to leave every 2 weeks with a feature limited yet functional spacecraft. And so by doing that, it's forcing us to integrate modules from week 2, right? Or week 4, because we maybe that's the second module ready. And then the things that we do earlier, the things that things plug into, so they're your core, your centralized services, your middleware, and so you're testing some of your most risky components for many times longer than you would have if you had done a couple of passes through some procedural tests at the end of a development program.
Good, very good point. Now we have Ibrahim and Doug.
Yeah, from the cost perspective, can you comment or share your experience and exposure outsourcing the development to good places like Israel, India, and Ireland, where some of the good software come out from? Thank you.
So just so I understand the question, are you asking to talk about some of our experiences from outsourcing and how that's worked with these approaches? Is that correct?
Yes.
All right. So given the work that we do, we haven't ever outsourced overseas, but we do work with geographically dispersed teams. And what I mean by that is we have members of our teams, we have customers that are not located in our offices in Melbourne, Florida. Excuse me. And so what we found is we've found that utilizing tools have been the most effective way for us to coordinate work across these groups. The concept of a sprint is, and I talked a little bit about it, but it's this time-boxed 2 weeks. You run through a whole tiny development cycle on a small amount of scope within 2 weeks, right? And so what that means is that you are doing development, you are integrating with components that other members of your team are working on, you're testing it, and you're putting out a release every 2 weeks. And so that drives collaboration. And so when you have teams like we have on Sunjammer in, let me think about this, Southern California, Austin, Texas, Melbourne, Florida, and sometimes up here on KSC as well. When you have these teams that are spread out like this, the fact that you know that you've got to get to you only have a couple of days to get through your design, to get to your implementation, to get your integration, that's encouraging you to talk with these. It's encouraging you to work to make sure that when things are done, they come together, they integrate well. And so very quickly, we utilize a couple of tools. We use an online wiki tool called Confluence. It's made by a company called Atlassian. We're able to host that internally. It's essentially secured. It's a secured system that you can log into, and anybody can edit any of the pages. They're all web pages. We utilize their issue tracking tool, Jira, that enables us to highlight something, identify it, assign it to somebody. They can go there and they can see. They don't have to be. We don't have to like actually tell them. Mm-hmm. Crucible and Fisheye are peer review tools, so they're online. All of these are internet accessible through an encrypted link back to our server. So you can, any member of the team can go in here and they can do things like hold a meeting, provide feedback asynchronously. It also helps with collaboration with the team.
Cool. And Doug had a question?
Partly you answered this, but at what stage, basically the software and the processor's role is to connect pieces of hardware. Mm-hmm. At what stage do you actually connect these to hardware, which may not have been developed yet?
Sure. Yeah, well, I'll expand upon that a little bit to say it's connecting to hardware, and then it's processing information, right? And so very early on, what we will do is we design these blocks at a high level. That's the preliminary design phase that I showed before we could start going into these iterations. And at that point, we have enough information that we can start defining the interfaces in and out of these blocks. And so you'll take a system that say, let's take attitude determination, right? It's taking data from star trackers and sun sensors and IMUs. It's ultimately interacting with actuators, reaction wheels, torque rods, cold gas jet thrusters, etc. And so when at the very beginning, we'll design these processing elements. We might simulate them in MATLAB in the case of attitude determination, but then we'll create data sets that enable us to start testing the data processing, the information processing side of that, until the hardware development team has got their components ready, or we've acquired one, we purchased something off shelf. So so by the time we get to actual hardware integration, we've already done some level of testing of informally with the information that would come out of these devices. And then as soon as the hardware is available, then we plug it together in a flat SAT in the lab and start working through interacting with the real devices as well. One other thing that we do, it's not as related, but it works well for us, is we utilize simulation as much as we can. So we'll actually, if we have time on a project, or if we have an intern that can do something, or needs a little side project, we'll have them develop little simulation tools. So they'll read the ICD for the sun sensor, for example, and they'll generate a little tool that outputs data as if it were coming from the sun sensor. And that, again, it lets us simulate that interface. It lets the test engineer pass realistic-looking data because it meets the timing and data structure requirements, et cetera. It's using the same physical interface as the real sensor would into the real system. And again, that's just another way that we try to improve fidelity. Yeah.
We have a question from the back room from Ariel.
What percentage of your software do you think is overhead towards helping you utilize COTS electronics? And so, for instance, if you're using COTS and you're sensitive to radiation, that means you have a bit flip and a deep register.
Yep.
How much of your software goes towards making sure that you catch that, acknowledge it, and do something?
Yeah, that's a really great question. So the key kind of takeaway from that question is that you don't get anything for free, right? So even if you pull something, you find a library, you're able to utilize it, it's off the shelf. There's still some level of integration, some level of test, some level of peer review of this open source component that you're that you're bringing in that needs to happen in order for you to make it effective and reliable in a spaceflight environment. So excellent question. Let's see, how much of our code percentage-wise is related to that? It's maybe like 5% or 10%-ish, something like that. I mean, it's going to be in areas like our health and status system and our built-in self-tests. There's going to be interfaces that we'll develop to map the interfaces that we defined internally to the library that we are pulling in. So yeah, I'd say that we're probably somewhere in that range, maybe 5%-ish.
Let's get into I don't want to miss the other part. This is great, this discussion. We will continue this offline, but let's have Ariel and Kate respond to these questions. And actually, I'd like Rodrigo to join in also. I think to take it question by question might be kind of interesting. So why don't you guys start, Ariel and Kate, to question 1, the response to that.
This is Kate from KSC. In terms of the architecture, and let me know if I'm excuse me, not hitting the question as you desired. We have a rover outfitted with these solar panels. We'll have a lander, and then we have this instrument suite. So this instrument suite is really designed to get us as much information before we drill and then after we drill as possible. So this kind of ties in with question 3 as well. We have this neutron spectrometer on board on the outside of the payload that's going to allow us to understand, really target where we drill. So it's kind of that human-robotic interface that you're asking about. This is going to allow us to understand, since we only have 7-10 days, like where those hydrogen hotspots are so that we can most efficiently target that water that's at the surface or below the surface. In terms of the financial element, we on Resolve are using a modified CATS approach that I think we mentioned before. So this was actually an approach I believe was used on LCROSS and possibly even LADEE that's been really successful so far. So we're not designing the hardware from scratch. We're working with these vendors to modify their existing hardware. And it's been very much an iterative approach. You can see we started these analog missions back in 2008, I believe. So we've had many iterations where we've been able to, for example, in the mass spectrometer, reduce the size of the magnet and target, preventing heat from radiating to other parts of the instrument. So we've really been able to work closely with these vendors in such a way that really seems to work well for a Class D mission.
So this is a class, did you say Class
D?
Class D, okay. So the architecture, so the choice, for example, to develop the payload, and then, as I understand it, things have changed a lot over the course of the Resource Prospect or Resolve. So as things stand now, you folks at Kennedy are developing the payload, and the payload includes the instruments that you described today, and the drill,
right,
and the hydrogen that you're going to carry along for the chemical reaction, basically, that you want to take place to look at water capture.
That's right.
And therefore, the interface, I mean, in a sense, that's an architecture. Develop the payload, then have someone else develop the rover. So in a sense, that's an architecture. That's sort of one step up from systems.
Sure.
And a question I have about that is as a choice of an architecture, is the interface between the rover and the and the payload, since they're not necessarily developed in tandem, unless the payload, unless the rover is pretty well defined at this point. But then, is the rover defined? I mean, do you know what the rover is going to look like and who's going to provide it?
Mm-hmm.
Okay.
So for the FDU unit, we had the rover provided by Canada.
Yeah.
And so as we move forward, they are still a potential option. We have not yet baselined what our rover option will be. But because our science payload is pretty mature, given that we're still in this phase A portion of the mission, that interface, I believe, in my opinion, not at the systems engineering level, will be easier in the sense that we have our requirements pretty solidly defined at this point, and the science payload is very mature. So we have really solid interfaces to pass along to that rover.
So that's going to put a lot of requirements on the rover. Implicitly going to mean that you're going to have a certain kind of rover to put your payload where you need it, to create the places where you can have access where you're going to need it. And the instruments that you're carrying, are these, I would like to know a little bit more about them. Maybe there's a link or a person I could talk to, but are these instruments that have already been developed? Is the infrared spectrometer, for example, and the mass spec, these have heritage from what development? Have they been flown before?
The neutron spec, I believe, help me out with this, Ariel, in case I'm wrong. The neutron spec, I believe, flew on L-Cross.
Okay.
And possibly.
Neutron spectrometer? Did they have a? I don't think. Did L-Cross have a neutron spectrometer?
If it wasn't a neutron spec, then it was definitely Nervous. I know that one of those two is heritage.
Okay, so it was probably the IR spectrometer. Yeah, and that's sort of a broadband IR spectrometer.
Mm-hmm. It has a short and long wave. I'm trying to think in terms of the mass spectrometer. That is not. I don't believe that has a balloon flight heritage from JPL. Actually, they flew that on a balloon, so that was initially developed by JPL.
It's probably a neutron albedo instrument, isn't it?
Say that one more time.
Is the neutron spectrometer, is that a neutron albedo instrument?
That I'm not sure.
Yeah, it probably is. Because that way you could actually, that would really allow you to get a lot more information.
I can definitely check that.
That takes some math. Maybe not. Maybe it's just a plain neutron spectrometer. I don't know. Yeah, could be.
I may add here, this is Rodrigo with Pisces. I think the tests that Ariel and Kate are talking about, some of those were developed or performed out here at Mauna Kea in Hawaii. And the Canadian rover she's talking about, excuse me, is the exact same platform that we just received also from Canada. So our objective, one of our objectives, is to be working with groups like Ariel and Kate, and providing that mobile platform upon which they can test their payloads. Like I said, it's the same open deck rover that was tested prior with Resolve here in Hawaii. So one of our goals will be obviously to get we will provide a mobile platform upon which different payloads and instrumentations can be integrated in, and then be able to provide remote links through a secure server to places as Canada or Kennedy, where they can control and operate the rover remotely with our support here in Hawaii.
So, and Russell has a question. Okay. So, and also clarify for me, you are planning on telerobotic operation on the moon, correct?
Yeah, when it gets to that point, eventually, yes.
Okay. So, and that has a lot of overhead associated with it. That's one of the reasons
right now
why
we're in the process of developing both remote navigation software and hardware, and the next step will be to develop some autonomous navigation capabilities as well.
Okay. I'm Russell, and then Tom.
Yes, that was just kind of this discussion brought up, and then you kind of got back to again calling something overhead. One of the principles. Design principles, architecture principles of something like a Class D mission is well represented by the Resolve payload. And it's the idea that you kind of over-instrument these prone to failure or experimental systems. Because, so they said, it's like half of their instruments could fail and they would still be quite successful. Or that it's like the amount of it, they're looking, they have the two instruments looking at where they're going before they drill and after they drill, and they've got a lot of information about what happened in the process. If you had a more optimized system, you could probably say, oh, well, we don't need that much observation. But one of the things when you're it's kind of the Scrum model again, is you're expecting things to not go the way you expect. And so in the old hyper-optimized model, it would look like waste or overheads. Like his 5% is building these extra interfaces. To some extent, that's not necessarily overhead. To some extent, we're using this bigger tool and we're getting more flexibility than we would need if we had optimized the system, but we haven't optimized it. And so if this is great, we can try something different.
It's just a telerobotic operation
no,
is expensive.
Right, no, yeah, no, I know
takes
that.
lots of resources.
In that context.
Lots of bandwidth and,
Right.
yeah. That's
But at
why
the
I'm
same
not
time,
around.
it's more flexible. So it's,
Well, yeah, and the issue that I brought up about the Apollo effect, when you can figure out a way to keep the humans in the loop, even though there is an overhead associated with it, that means you could actually collect reasonable samples.
right.
Yeah.
And so that's
a trade space.
It's kind of a generalization. When going to the Scrum model, going to the Class D model, there's a lot of activity that other people might call waste. Like writing 5 prototypes before you decide on what the first one's going to be. A lot of people say, well, why did you write 5? You knew what you were supposed to do the first time. It's like, well, you don't know until you try. And so there's a kind of a stylistic way of doing this, overlapping instruments where you're getting more information than you really need if it all works perfectly. But if some of it doesn't work perfectly, you've got ways out or ways around that you wouldn't have if you, again, simply optimized everything to the nth degree. So that was one aspect of this that just kind of jumped out at me, that you were talking about the architecture and the stylistic difference of the way you architect things in the Class D realm that I wanted to point out. And then kind of when we move on, I had another point to make, but it's not quite relevant to this.
And Tom had a comment?
All right, we need to kick this architect idea up a couple of notches. Recently, we basically blasted our way through Asimov's 3 laws of robotics with a hot 50 cal. So we're going to have to come up with new rule. And the one I'm proposing is maintain the human-machine symbiosis. That is to say, you have to present your project as a symbiosis between humans and machines in order to be anti-fragile if you don't want to be canceled. And that we then have to move to maintain that. And we just lose, we are not building machines, we are building human-machine symbiosis.
I agree, and that means that you want to use machines to their advantage and humans to their advantage. And there are times when working together they can do things, and there are times when it makes sense to have them completely and entirely separate.
And when the mutual is stronger than the 2 individuals, then you've got the symbiosis. It turns out the word isn't very strongly defined, so we can define it as we go along.
Thanks. And Ariel, did you want to make any comments? Or?
Mine was just on question 2, which I don't know if you can scroll down.
Oh,
so I can
great.
read
So
it again.
question 2 is good. Let's have you guys comment on question 2, and then we'll go to Dave. Dave comment on some of the things he talked about.
Yeah, and this came up a little before, but the capability right now is water and a few other things, but really water. Like we're using several instruments. They're all different though. Like it's not like we're carrying 2 NSS. Right. We're carrying 1 NSS and 1 nervous, and they sense slightly different things. So we have lots of different ways.
They're very complementary.
Yeah, that we're gonna see water if we see water. And the progress between now and the next 5 years, like we hope to launch within 5 years. And so, yeah, we hope to get much smaller, as small as we can. And the work that we're doing, like Kate said, we're using COTS models, we're trying to optimize them, we're working with vendors to use them. But we don't see any reason why these same components can't go to other harsh environments. There's nothing special about the moon. It's harsh.
So what are your sort of operational limits? Are you planning on surviving during lunar night or actually operating during lunar night?
My understanding of the concept of operations is once we get to the surface, we are all on all the time until we're dead.
Okay.
So
what's your, any place to find out what kind of thermal design you're using to make that? Of course, you're designing the payload, and so you're assuming that the rover will essentially provide you with the thermal protection that you need to
yeah, we have a
operate during lunar night.
thermal engineer that works that we work with from JSC.
Mhm.
So we just do what he says.
Because that's, especially if you're talking mobility, and I mean, and then the peak power requirements for operating. I mean, the people that I know that have talked about robotics rovers for lunar night talk about hibernation strategies for at least part of the night and maybe limited duty cycles. It's challenging to do a complete, to be able to operate fully. Russell needs a microphone, and then Doug, and then Russell.
I just wanted to follow up on what Russell said. The overlapping measurements may very well handle failures, but they also handle physics that isn't known. You get in there and you say, I know what's going to happen, and therefore you define them as overlapping. If it turns out that nature is not exactly as you think, then they may be giving you very different information, new information.
Well, I agree with the complementarity in payloads because the combination of neutron spectrometer information with the infrared information, further analysis with mass spec, is going to provide you with a much better understanding of the data you get from any one instrument. So that's like constraining a problem. It's critical to be able to do that. Yeah.
Yeah, this is kind of another way of saying anti-fragile. It's that you go in there, you build things that are more flexible than you would think they would need to be, so that when things are different than you thought, you see stuff you didn't think were going to be there, and so yeah, it's a nice way to put it, and point out that that's the expectation. The other thing was what I know of Resolve is they're planning on the dash capability. You can go into the shadows for short periods and then jump back out. And you're right. They're going to have pretty strong control over the system until they don't, and then they're dead. But yeah, that's what they're saying. That's why it's 7 to 10 days of sun, really short drives off into the shadows until they figure out what those limits are. But basically, they're not trying to survive a harsh environment at all. They're trying to, is it non-harsh to go in the shadows for 30 minutes or is it an hour? They'll kind of discover that when they're there, and they'll have some decent models. But that's the way I remember it from last year's presentations. They were designing it so that during that 7-day period, that would be pretty, not major swings and not all that radical compared to just the environment they're going into in the first place.
You do want to have solar power when you're drilling, probably. You want to have direct power.
Yeah, I don't know how they were going to handle that. It didn't all add up just yet. So, but I'm sure they're getting closer. So yeah, so the exact methodology will be interesting to see what they do.
Actually, we were hoping to get a presentation on the Canadian concept for the rover today, but that, for a variety of reasons, the speaker couldn't make it. So.
The other comment I wanted to get to, and we're kind of beginning to run out of time, and I want to bring this up because it goes back to, again, the design methodology and another way of what does kind of Scrum look like. And your question is, how do you avoid mass creep and mission creep? And so I wanted to bring up a methodology I learned back in flexible manufacturing, and that's part count is a really nice metric to just drive things like mass and reliability and a number of things get much better. And the example that I studied ago was a Japanese company, and I think it was an air compressor. And so they disassembled it, and they laid all the parts out in the floor, walked by the system every day, and anybody could put up a suggestion of how to reduce part count. And over like 90 days, they went from, I think it was 300 parts to 70 parts. And when you're at the end of a process like that, it's going to be more robust. It's a critical parameter. And then the other principle of that is, again, how you do a Scrum in the context of a well-documented process, is you kind of stop that for a little while and say, for the next 90 days, we're not going to do this. We're just going to push on it really hard. And when we're done, we'll put it back together again.
If you really explore the process at the beginning like that, if you really open up the potential exploration space early on and look at different mechanisms, for example, you're not as apt to keep on making components larger and stronger all the time because you're terrified that something's going to rip itself apart, which is typically what happens. And the athlete, by the way, is a perfect example of things getting bigger and bigger to the point of almost ridiculousness,
Yeah.
in my opinion.
Yeah, that's it. But this is also another value of modularity. When you have modules, you can do that. You can excerpt the module, put in the black box
Yeah.
for the month while that team is going, saying, okay, can we get 10% less mass? And we can do anything we want to for the next 30 days.
Yeah.
And when we're done, it needs to work again. And so you can create these little exercises where you can do agile stuff in a limited time, in a limited way, because you have the modular design, and the way to confirm that when you plug the module back in, you have a well-specified process of how to reintegrate it.
Mm-hmm.
And so that's another aspect of how you would do agile in this very restrictive environment.
Yeah, well, that way we're actually paying attention to the interfaces between the different components from the beginning, and not waiting till the end to actually do that, which is a really good thing. And we have another question, because I want to get into also looking at financial and political structures that can support the kinds of things we were talking about this afternoon. And I wanted Dave to make some comments on that. But we have another question in this area. We got about 10 more minutes. Maybe not quite. Is it not quite 10? Last time I looked, it was 15. Yeah.
So I actually have a question for
Okay.
you.
Oh.
And it relates to what we were talking about earlier with your use of the Scrum model on avionics and what you found with that. Because we have tried that, and we found that we could not keep to a 2-week schedule. And even when we lengthened it, it seemed that we lost some of the energy that was sort of inherent in 2 weeks. But because of hardware, fabrication, manufacturing, and assembly issues, it wasn't just a person writing code, it was a person trying to interface with the whole infrastructure of, in my case, Kennedy Space Center, trying to, implement and test an idea. And so I'm wondering how you mitigated those problems or got around them, or what lessons you learned from it.
Yeah, that's a great question. Trying to think on a couple of projects and how we've approached this problem. We're actually working through this right now, also on Sunjammer in particular, specifically. Actually, a couple of projects. You touched on a kind of an interesting point about the sprint with having those for lack of a better word, those deadlines periodically. The fact that you're constantly on this chain where you're developing something small, but you're developing something or designing it, developing, implementing, integrating it, testing it. It gets you onto a pattern that eventually you get to this point where it feels like a fairly high level of productivity, but fairly consistent. Yeah, and so I could see how if you say stretch that out, how that could. How some of that motivation or energy could certainly be decreased, or seem like it's being decreased. All right. So to answer your question, so we've approached this in a couple of different ways. I mean, on some projects we already have the hardware, and in which case, however we choose to split up, segment the software development, it doesn't really matter because the hardware is there. It might be that they've done an initial checkout of the hardware and maybe if we find an issue and we could provide that feedback to the electrical team. Sometimes that happens. Sometimes sometimes the electrical guys are out ahead of us. Other times, like is the case that we're working through right now, is the electrical boards are coming in sync with our development schedule, and so we may not have the hardware by the time that we start. And so what we've done in the case of the avionics boards for Sunjammer is that we've taken an approach where we've taken the scope of development for the avionics board and we've split that up and kind of pipelined it, is probably a good way of putting it. We've pipelined that effort, starting out with requirements definition in the very beginning, of a sprint, and then when the test definition for when the board gets in. Then we work through an initial implementation, and we'll do a couple boards in parallel since we're pipelining. We'll work through the implementation of some of the features, and then once the boards show up, now we're doing a test. We'll wait till align sprints, but then we'll do some tests. We'll do some checkout. We'll provide feedback so that they can take that. Take the test or the code that we've written and use that so that they can do more rapid iterative testing in their own labs, and then which that we can build. And the reality is, if they don't, then we switch over to another board that we can actually make forward progress on until they do. So to summarize, we spread out the development that we would maybe have done for one board in one sprint with the whole team. We spread that out. We try to pipeline or interleave development of a couple of different avionics boards. We have 5-ish, Kira, something like that, 5 boards. And we'll interleave them, and then we try to, in that first version of software, we try to give enough functionality in that wherever that time's going to end up with, to give the hardware team something useful that they can use to do their own quick testing of their electrical designs past the first revision of the board. Sometimes it's perfect the first time, right? But the real world is often it's not. And it's no comment on the electrical guys' ability. They're highly capable electrical engineers.
Thanks. I want to make sure Dave has a chance to speak. We have about 5 more minutes. Can we hold your question so you can talk to Dave offline? So Dave, I want you to address the issue of what kind of financial and political structures can support the kinds of things we've been talking about this afternoon.
Well, I think the strategy is to build on the resources that currently exist and to increase the level of collaboration and the level of communication. And what we've been doing really for the first year, began at the League meeting in 2012. And as a result of my having met Russell there and heard his thing, I got very excited about his idea. And then I said, well, gee, this is something that we ought to try and bring to a lot larger audience. So, I was talking to Pam and Russell and said we should have a poster. So we went, the next stage was to try and put our poster out. We did that last year at the Lunar Planetary Institute Science Conference, also at the Survey Conference, which is a virtual meeting, and then we also had a poster at the 2013 League meeting. So we're also extending that by trying to include some additional conferences this year, as well as what Fluxure itself is doing directly. So, having a SIG to look at that is a way of trying to pull in other people into an active collaboration. But we're again going to the Survey Network, and Russell will be going to the London Lunar Symposium. I'll be going to the International Astronomical Conference in Toronto, which is a very big international meeting. The National Space Society is a nonprofit agency with the United Nations, so there's a connection that we have with their ECOSOC committee, and we have the right to give input to committees like COPOS, the Committee on Peaceful Use of Outer Space. So, these are where ideas circulate and where you meet people and where you kind of network. Certainly trying to spread this message and this type of collaboration among NASA centers here at Kennedy and at Ames and Goddard, Johnson. There are people who are looking at these kinds of approaches. So building on the assets that are there. Then there's the intellectual foundation. A lot of work is going on through League. They have a League roadmap, and that builds on a National Research Council report, the scientific context for the exploration of the moon. There's also a movement to have strategic knowledge gaps, and coming up in April of next year, they're going to be updating that. So this is very representative of the lunar scientific community. A lot of work and foundation is there. So, the bottom line is having, the lunar science community say, well, here are our objectives, here are our priorities, and these are the targets. Then you take a look at, well, what is actually feasible at the lunar cube scale that we're talking about. We can look at what are practical targets that can do useful, significant science. So those are certain ways. The International Union of Geodesy and Geophysics that I mentioned, I've tried to make some inquiries find more about their politics. I am not an emeritus professor, as you usually have to be if you ascend to, become the head of your national committee. But this is a very well-recognized international scientific organization that has the heritage of it. So this is, at least in planetary science, trying to use those networks that currently exist. The commercial on-ramp is another existing foundation. So some of the connections that we're looking at building on include MoonX and Astrobotic. So these are our American companies, and the Google Lunar X Prize Foundation is another very significant chunk because they have this international scope of activity. So, you know, that's kind of the trade space of who and what constitute the lunar community, and how can we raise the bar, how can we do more for less, how can we bring a new range of countries in and people with new resources into this framework. So those are, you know, I probably exceeded my 5-minute time limit, but I'm hoping that kind of addresses the thinking strategically about how we're going about. Now, also we've identified people we would say are poster children for this approach. And Doug is certainly one of those. He's gone and knocked on the doors of different people internationally for his project. And of course he has to convince them that this is good science that he's proposing to do, and he has something that's cost practical. Ian Garrick Bethel is certainly doing something similar. His Lunar Swirls mission is also a collaboration with the Open University College of London and the Kyunghee University in Korea, with some hope that there will be National Space Agency funding in that area. So, you know, those are examples. Lunar Flashlight is a third. Well, that's a NASA-sponsored contract.
It's similar.
So these are, you know, these are examples of people who are trying to go and look at international collaborations for small, cost-effective approaches. So that's, you know, that's kind of a thumbnail sketch of what we're doing. And, you know, we want to do good science. We want to prove good price points, that we're lowering the price point, increasing the access, and we want to increase the collaborative model that we're doing and the commercial model.
I think you pointed out that how important the CubeSat paradigm is, which has, you know, all the same players, but new relationships between academia, the private sector, and government. There's a role for everyone to play, and I think it's been critical in making what we're seeing now happen. So for deep space. Yes, one final comment. We're really kind of over time, but from Doug and then from Tom, relatively quick. Oh, okay, sorry.
All right, we need to kick this up a notch again. There is an analysis available of the political situation that clearly explains the whole thing. It is called Frames of Reference. It was developed by a professor from Michigan named Backlake, who is slightly to the left of Karl Marx. But it was never used by the left. It was always used by the right. The Fox News Network is what it is because it is a frames of reference design intentionally.
You know, it's like we were talking about with the interleaving of the boards. It's, if you can't do what you want to do, find something you can do.
Right.
And you're always in motion, and so it's find a smaller, cheaper mission that can bring in a partner. And so, you know, if you want to engage the rest of the world, then go find some inexpensive thing that the Chilean or someone in Poland can work on, and you're moving forward. And because, as you pointed out, it's the same relationship. So the human context and the collaborative context is getting moved forward, even if it's a $100,000 piece, not a $1 billion piece. And then, because you're using such small potatoes, you can kind of get around some of this big politics stuff. But I don't want to go there. But yeah, it's that idea of find the version of one of my physics professors had of this was, if you can't solve a problem, create a simpler problem that you can solve. And so that's this one. So now you get
For the last comment, we have Doug.
Well, rather than escalate what Dave said, I'd rather de-escalate it and address the SIGs. I think one of the things I have seen in this is that there are frequent questions that we don't have the people to answer. And so my suggestion would be that everybody in the SIG be encouraged to talk about it to 5 other people. And that may very well be a way to bring in more people.
Thank you guys for quite a lively discussion. I'm really pleased. And we are about at the end of the day. And so a reminder, please, if you're leaving before dinner, which would be so silly, please make sure you go review the board, take pictures of any postings that are relevant to you so that you can continue building relationships here. If you are involved in CubeSats in any way, or if you just want to continue being involved in this kind of a conference where it's not just the delivery of what people are working on, but also the interactive opportunity to build upon what you're hearing. In October, we will be in Sunnyvale, California, doing our 4th International Workshop on Lunar Cubes. If you fill out a form and turn it today or tomorrow, you will get a 25% discount. I understand somebody had an old form. It's a 25% discount. Sorry, but still, that's pretty cool. We have the evaluation forms, and Faith, can you and Joanne hand those out, please? And please give those back to us, because we really do take what you say into consideration, and where we can, we do incorporate your feedback into what we do next time. If you're leaving and you're not, even if you're going to be back tomorrow, if you leave your name tags with us and your table tents, we'll take good care of them. You don't have to worry about where you put them or what you do with them. And I need mic runners again while you're filling out the evaluation form. What'd you get today? We set some intentions, we set some desired outcomes this morning, and I'd like to hear from you. Did you get some of what you came for? What are some of the highlights that you got that you're taking away? And the mics are, and you know that I'm going to call on you, so you might as well volunteer. So somebody that, Russell, why don't you start?
Well, my simple was I got to see the launch.
Yes, we did get to see the launch. They did do us well.
But yeah, just more integration, more ideas, more better understanding of the people who are here.
Pamela, what'd you get today?
Well, again, I mean, lots of interaction, lots of potential new things to think about, and building partnerships for the future.
Cool. Brandon.
Oh, what did I get to that? It was really great to get exposed to some of the other groups that are doing work on the lunar surface and lunar science. It was really great to see some of those, or see the various missions and the various groups that are doing studies, and then also to see how we spent a lot of time thinking about how we approach development in our group, and some of the stuff we talked about today has come out of just that internal research and decision. So it was very interesting to hear other ways in other domains how similar ideas like iterative development can apply. So those are all.
Thanks.
I would say highlight is probably Dave's discussion of the broader picture and how one might expand what we're doing, and also exposure to a number of areas that I really have not worked in.
Hi, this is Sushikant Marikonda from Advanced Magnet Lab. I think I got to learn a little bit more on the aspects of lunar science, but can I also give criticism?
Write that one down, unless you'd like to share it and get feedback. Yeah. Go ahead.
No, I guess one aspect I really wanted to hear was a bit more on how, in terms of the technology-wise, in the cryogenics and so on, in the material properties. Not really criticism, but it's something if somebody has a knowledge, or it could be part of future sessions, to include about the composites, the latest composites that are that can be used in cryogenic temperatures, and what are the impacts of long term. Because one of the severely hampering items.
Keep going.
One of the severely hampering items that we found out is the knowledge of materials that you can use in cryogenic temperatures is pretty limited. Even when you know something can work, you still cannot quantify them. The tests are not available. The data is not really available to use them for really analyzing and putting them in designs. If anybody has such a database or such a information source it would be nice to know.
Okay. So do you guys know whether James Fessmeyer and the Cryo Lab would be a resource for him? Yep. Yep. Yep, I'm running.
We contacted a number of people that could give presentations in cryogenics, and we've tried very hard because we're very interested in that area. So what I'd really like to have from you is a discussion where we could come up with some more names of people who could potentially be interested in coming and presenting on that topic, because it is really important, and thanks for pointing that out.
Cool.
The other thing is the other true answer is there isn't a lot of good data. That was why one of the projects we had when Greg Scharfstein was actively involved was called the Mobile Chamber, was to create a low-cost way to do a lot more testing at lower temperatures. And that's one of the things that, again, got me started. One of the reasons I started this workshop is precisely to begin getting that interest. Now that we know a lot of people are going to be doing a lot of complex work at 40 Kelvin, there's a need to learn a lot about a lot of things that we don't know very much about. Because most people, if they go down at all, it stops at 77 Kelvin. You know, it's either millikelvin or it's 77 Kelvin, and what happens at 40 is pretty unknown in many ways. So there is a need to encourage even that fundamental material science work. And that's one of the things we want to come out of it. So both Pamela's suggestion of let's go find who could do that work, and if they've got some, let's go get it. And then also, how are we going to vector more money into people doing that kind of fundamental material science research, because there's a lot of work that needs to be done, both from mechanical engineering point of view as well as the science point of view of how do volatiles work at 40 Kelvin, because almost all the study of volatiles is actually at much higher temperatures.
Thank you, Russ.
Since people are saying missing database, my particular interest would be knowledge of what happens when you have 40 years of exposure to solar wind. For example, what happens to AR coatings, what happens to this wonderful nano stuff that makes the dust slide off, what happens to MLI. I'm having to guess on all of this stuff, and if anybody has a source or direction, I'd be very happy to hear it.
Abraham? Unless, are we done with that wonderful discussion? Thank you.
Okay. Abraham from Flexion Engineering. Like this kind of creative ideas and cross-pollination of various knowledge share was quite exciting, and I find it's the more we kind of grow in this kind of a collective environment, I think it's going to be very, very interesting, and I'm getting sucked into various parts which I didn't even realize I'll be getting into. Thank you, guys.